Electrostatics, problems on conductors and dielectrics, series on electromagnetic field theory, lecture number 1.52. Conductors are materials with a lot of electrical conductivity, whereas dielectrics are materials with nil conductivity or small amount of conductivity. In the present session, the focus is on problems set around the characteristics of conductors and dielectrics. In the problems which we are going to tackle right now, we use certain basic relations pertaining to current, voltage and resistance. J equal to sigma E. Sigma is conductivity, E is field intensity, J is current density. The relation between J and E, it is called point form of Ohm's law. Current density at a point is proportional to electric field intensity. The proportionality constant is conductivity. J equal to sigma E, mathematical form. J, current density, I, current, these two are also related. That relation is given by I equal to J dot dA. Now potential. Potential at a point P in an electric field is given by minus integral infinity to P E dot dl. Of course, this is absolute potential. The resistance R is ratio of V to I. V is potential, I is current. Now we consider the problem example 1. Two long coaxial cylinders of radii A meter and B meter with B more than A are separated by a material with conductivity sigma mhos per meter and permittivity epsilon farads per meter. If they are maintained at a potential difference of V volts, determine current that flows from one cylinder to the other when its length is L meters. Also find the resistance R of this section of cylinders. The given structure is illustrated here. Inner cylinder radius is A, outer cylinder radius is B. In between the cylinders, there is a material with conductivity sigma. Potential difference is V. Length is L. Now, solution process. The field between a long coaxial cylinder set shown in figure, it is shown in figure here, is the field is given by this formula. E equal to 1 by 2 pi epsilon lambda by rho cap. First point we have to keep in mind is that this formula is in cylindrical coordinate system. Second thing is this can be derived within no time using Gauss law. Here lambda coulombs per meter is the line charge density on the inner cylinder. Using Ohm's law and Gauss laws, the current can be found as Ohm's law is J equal to sigma E, I equal to integral J dot dA. So I is closed integral J dot dA. Of course, J equal to sigma E. Therefore, I equal to sigma closed surface integral E dot dA. So, but E dot dA, according to Gauss law, it is Q enclosed by epsilon. Q enclosed becomes lambda L. Lambda is charge per unit length and length is L. Therefore, lambda is Q enclosed. So ultimately, I comes out as sigma lambda L by epsilon amperes. Resistance requires potential difference between the cylinders. VAB, potential of A, cylinder A, with respect to cylinder whose radius is B. VAB is B is minus B to A E dot dl. But E is known to us. Substituting and doing a manipulation in cylindrical system, we get VAB as lambda by 2 epsilon natural logarithm B by A volts. Resistance, therefore, can be found as R equal to potential difference by current. Potential difference VAB is lambda by 2 pi epsilon natural logarithm B by A. And current is sigma lambda L by epsilon. Ultimately, we get this expression, that is natural logarithm B by A by 2 pi L sigma. We consider another problem, example 2. Two concentric metal spherical shells, radius A and B respectively, are separated by a weakly conducting material of conductivity sigma mhos per meter and permittivity epsilon. When potential difference between the shells is V volts, determine current that flows from one shell to the other and also resistance between them. Notice the similarity between this problem, example 2, and the problem we tackled in example 1. Lot of similarities there. but that problem is set in a cylindrical system, or it exhibits a cylindrical symmetry, whereas this problem here, the structure exhibits spherical symmetry, except that the electrical physics of the problems are same. Let us suppose solution process. Let us suppose a source with voltage V is connected between the shells driving current. Let us also suppose Q coulombs be the charge on the inner shell. Then in the space between the shells, electric field is given by this formula. E equal to 1 by 4 pi epsilon Q by R square R cap. First point you have to keep in mind is this formula is in spherical coordinate system. Second thing is this can be found easily without much difficulty using Gauss law. The structure pertaining to this problem is depicted here. Inner shell, radius A, outer shell, radius B. This is source, voltage source connected. Now, the potential VAB, the formula is minus B dot dA E dot dl, but E is available in spherical system, so dl also has to be expressed in spherical. R dot dl is dr, therefore VAB becomes minus Q by 4 pi epsilon integral B to A 1 by R square dr. So integration, performing integration and all that, we get Q into B minus A by 4 pi epsilon AB. This is the voltage between shells, but it is equal to V. The potential that is connected is V. Therefore, VB is Q B minus A by 4 pi epsilon AB. From this expression, Q can be found as 4 pi epsilon AB V by B minus A. To find the current, it requires evaluating the current density over a surface enclosing the inner shell using Ohm's law and Gauss laws. As we did in the case of previous problem, it is possible to express I. I is J dot dA. This is the current density relation, and J equal to sigma E, that is Ohm's law, and E dot dA, it is Q by epsilon, Gauss law. Resistance R is the ratio of voltage to current. So R is V by I. V is available, this is V. I is available, this is I. Therefore, V by I is B minus A by 4 pi AB sigma. For large B, when the radius of outer shell is large when compared to radius of inner shell, the second term is negligible. What is this second term? This A. B by something minus A by something. Same thing. When A is small, the first term is dominant and second term is negligible. So B by 4 pi AB sigma is approximate value of R. BB gets cancelled. So it becomes resistance is 1 by 4 pi sigma A when outer shell radius is large when compared to inner shell radius. Another problem, example 3. In a free space region Z more than 0, the voltage is specified as V equal to 15 Z power 5 by 3 volts. Determine A, field intensity E, displacement density D, charge density rho, and also current density JZ at Z equal to 0 and Z equal to 1 meter when velocity, charge velocity BZ is 5 into 10 power 6 meters per second. So potential is given in a certain region and we are asked to find out field intensity, displacement density, etc. etc. Solution process. A, field intensity, displacement density, charge density. Of course, once field intensity is available, density can be found within no time by multiplying E with epsilon. And once D is available, D is from D, rho can be calculated by considering its divergence. Okay. E equal to minus grad. This is the differential relation connecting scalar potential with electric field intensity, and expansion results in this quantity. V is given, V equal to 15 Z power 5 by 3. Substitution and performing differentiation, we will be getting E equal to minus 25 Z power 2 by 3 Z cap holds per meter. Displacement density is D equal to epsilon naught A. E is available, simply multiply with epsilon naught, we will be getting D. Now we want charge density rho. Rho is del dot D. D is available. Now apply divergence over D. It results in minus 2 by 3, 25 epsilon naught Z power minus 1 by 3. A little bit of manipulation leads to rho equal to minus 147.57 Z power minus 1 by 3 picocoulombs per meter cube. Current density B, JZ. J is rho charge density, velocity, direction is of course z direction. Now we have rho Vz is given, therefore J becomes multiplying these two quantities, we get minus 737.83 Z power minus 1 by 3 Z cap microamperes per meter square. Hence current density is 0 at Z equal to 0. From this, Z is there. Hence current density is 0 at Z equal to 0 and it is equal to minus 737.83 Z cap microamperes per meter square at Z equal to 1. By putting Z equal to 0 in this expression, we will be getting current density at Z equal to 0. By substituting Z equal to 1 in this expression, we will be getting current density at Z equal to 1. We consider another problem, example 4. The inner and outer radii of thick spherical shell with a conductivity sigma equal to 0.05 by R moles per meter, or R1 is 3 cm, R2 is 8 cm respectively. These are radii of spherical shells. It is carrying a radial current I equal to 4.5 amperes. Determine voltage and resistance between the spherical surfaces and also power dissipated between the shells. This structure exhibits spherical symmetry. It consists of two spherical shells. Now, solution. Conductive spherical shell with the dimensions is shown here. Okay, radius is 3 cm, inner radius, outer radius is 8 cm. Conductivity of the material that exists in between the shells is this one. A. Voltage and resistance. Current density is current per unit cross-sectional area. J is current flowing from inner shell to outer shell or outer shell to inner shell, and the area is 4 pi r square. So actually the idea is this: current is given 4.5 amperes. The current is same wherever you consider, current is same, but current density, suppose I want current density somewhere here, then you have to imagine a spherical surface with a radius equal to distance of this point from the center. Let us suppose that distance is r. Then current density at this point is current, that is 4.5 amperes by area of the spherical shell, imaginary spherical shell whose radius is r, that is 4 pi r square. Now what we got is 0.36 by r square r cap amperes per meter. This is current density. Electric field intensity then is E is J by sigma. J is available. J equal to sigma E is Ohm's law. Therefore E equal to J by sigma. J is available. Sigma is given. This substitution results 7.16 by r cap. This is field intensity at this point. At a point, arbitrary point in between the shells. From this expression, field is radially outwards, implying the inner sphere at higher potential with respect to outer one. This potential then is V is equal to minus 0.08 to 0.03 EDR. Actually, it is E dot DL. The structure is in spherical system. Formulas are in spherical system. So we have to tackle the problem in spherical coordinate system. So performing integration results in V being equal to 7.02 volts. V is available, I is available. So therefore, I is given. R is V by I. V is 7.02, I is 4.5. Ultimately, we get 1.56 ohms. B. Power dissipated. Using Joule's law, power dissipated is, this is Joule's law, P equal to integral E dot J d tau. D tau is differential volume. But we know J equal to sigma E. So substituting sigma E for J, we get this expression. We are doing this integration in spherical system. So substituting appropriate limits and evaluating the integral, we get P as 31.52 watts. Of course, it can also be computed from I and R. P equal to I square R. R is available, I is available. One can compute it. We got almost same results, 31.59. But this is finding power in circuit theory way. We consider another problem, example 5. The potential in a region is given by V equal to 15 Y cube plus 3 Z. Determine field E at surface Z equal to 0 and B. Show that Z equal to 0 is equipotential surface C. Find the total charge within the region 0 less than x less than 2 meter, 0 less than y less than 3 meter, and Z equal to 0. Outside Z equal to 0 surface, assume epsilon equal to epsilon naught and V is more than 0. Solution. A. Field E at the surface Z equal to 0. We use this formula E equal to minus grad V. V is available given. So E can be computed without much difficulty. After differentiation, we can have E as minus 45 y square Z y cap minus 15 y cube plus 3 Z cap volts per meter. At Z equal to 0, E becomes equal to minus 15 y cube plus 3 Z cap volts per meter. Now B, potential nature at Z equal to 0 surface. At Z equal to 0, potential is V equal to 0. Potential V equal to 0. See, this is V. When Z equal to 0, V becomes 0. And hence, planar surface Z equal to 0 is an equipotential 1. All points, V0 means all points over the surface are at one potential. Of course, it may be 0. So therefore, it is an equipotential. C. Total charge in the region X in between 0 to 0 and 2, Y in between 0, 3 and Z equal to 0. The electric displacement density or electric flux density at Z equal to 0. D is dz is epsilon naught E. This is epsilon naught. E is available to us. This is E. So dz is minus 132.81 y cube plus 3 picocoulombs per meter square. Charge enclosed then becomes Q is integral d dot dA. We are doing this problem in Cartesian, so it becomes integral dz dx dy. Substitution results, manipulation substitution gives us minus 8.564 nanocoulombs. These are some of the problems which I want to discuss with you right now. Note, all these problems are around Ohm's law, Gauss law, potential, differential relation connecting potential with field intensity, Joule's law. These are all fundamentals or basic laws of electrostatics. Enough.